So last time we started the calculation for the specific heat in the solid state materials due to phonon. Okay, so we know there are phonons in the solid, where this phonon modes are contributed from the lattice vibrations, and we can second quantize lattice vibrations, and we define this phonon mode, normal modes, and also define the phonon creation destruction operator A and A dagger or B and B dagger. So today we will continue going along this line by calculating the specific heat contributed from the phonon. For example, this phonon-assisted tunneling through the tunneling barriers of a solid where some kind of energy is actually injected, and the phonon could actually contribute to the tunneling where this phonon energy is absorbed by some kind of incoming particles hitting on the target, and it gives rise to the increase of the final energy from E1 to E2, and we could calculate the probability of such events, which is proportional to the density of states, d of omega, times this small windows of the frequency difference, which is given by the energy difference between E1 and E2 divided by h bar. So the Debye model is a way to estimate the density of states near the small momentum transfer limit of a phonon mode. Okay, and our goal is to calculate thermal averaged total internal energy E bar, and take a temperature derivative of this E bar, and you get CV, specific heat. And E bar is nothing but ensemble average of this system, where the Hamiltonian of this phonon, free phonon, is given by this quantized phonon energy h bar omega q multiplied by the phonon energy operator nq operator plus 1/2. All right, so the nq with it rearing ahead is defined as the number of phonons or number of bosons for each normal mode variables q, and you sum over all the normal mode variables. All right, so let's just follow the standard statistical mechanics to calculate this E bar, by plugging this, phonon Hamiltonian, and then after this, kind of simplifications, we could get this simple form where this E bar is nothing but this h bar omega q times nq bar, where nq bar n plus 1/2, where nq bar is nothing but the average phonon number, which is nothing but Bose-Einstein distribution function. Okay, because phonons are bosons. Okay, so they satisfy these commutation rules for boson. So we could plug in this nq bar and back into the E bar and take the temperature derivative of the E bar, and we get some messy temperature frequency dependence of this CV. And we could change our variables from this summation over Q to integration over the omega by a change in variables that you are very familiar with from your Introduction to Solid State Physics 1. Where the only thing that we need to worry about is density of states, the omega, and we know very well from the solid state 1 that for a three-dimensional system, we could calculate kind of a number of electrons in the Fermi sphere, and when you sum over all this electron states inside the Fermi sphere, you get a total number of electrons, n, right? Okay, and which is this kind of a small volume inside this Fermi sphere multiplied by this kind of a 4 pi k cubic divided by 3. Okay, so and you could very easily take the dn by d omega, you get density of states per unit area and per unit energy, okay, which is nothing but k squared dk d omega multiplied by a prefactor. All right, so then we could, plug in this d omega here to evaluate this frequency integration. However, this is a kind of a trouble here because dk d omega is not that well known because remember we have acoustic phonon and optical phonon. Right? For acoustic phonon, there's a sine QA/2 dependence of this omega as a function of momentum q. So, if you take dk by the omega or dq by the omega, you get complicated functions, so sine and cosine function. So, to make further progress and to simplify this calculation, Debye invented, or took the approximations. Okay, so it's called the Debye approximation or Debye model, where you know very well that this acoustic phonon mode shows almost linear relationship to this momentum k or q when k is very, very small. Remember that. Okay, so because sine k/2 is linearly proportional to q or k when q or k becomes very, very small, and this is how Debye could simplify the tensor space by assuming that omega is linearly proportional to k with some prefactor c, which is called sound propagation, sound velocity. Remember, acoustic phonon mimics the propagation of the sound wave, and c refers to the velocity of the sound propagation. So, based on this Debye approximation, we could further simplify the tensor space profile as a function of omega. For example, in the realistic materials, the tensor space of phonon mode as function of omega may look like something like this, curved region here. And of course, this is very hard to calculate if you want to integrate, plug in this very complicated, formula for this tensor space. Okay. However, under the Debye approximation, we could very much approximate this kind of a weird shape of a tensor space profile by, a curve like a rad, which is a quadratic in omega. And then, beyond this omega d, we call this Debye frequency. There's no phonon mode. So of course, there's a higher energy cutoff. Beyond that energy or frequency, there's no phonon. Okay, so the phonon tensor space exists only within certain range in frequency domain. Of course, because the phonon energy cannot be infinity in the realistic materials. Okay, so it has to be cut off somewhere. Okay, and this cutoff frequency is called Debye frequency, which will cut off the tensor space distribution as a function of omega. So let's just derive this omega squared dependence of the tensor space under Debye approximation. Okay, so remember that under Debye approximation, omega is actually c times k. Okay, so the total number of states within a window of frequency is given by d omega times, capital D omega times small, frequency difference d omega, which is the same as the total number of states calculated in the Q space, right? A capital D of Q times little delta Q. That just comes from the conservation of density states. So it doesn't matter how you calculate density states per unit, frequency or in the Q space. Okay, So in the Q space, it is proportional to delta Q vector divided by this small volume, okay, 2 pi over L cubic term in the denominator, so which is proportional to Q squared dq. But you know very well that this omega is linearly proportional to K or Q, and as a result, this the omega is also quadratic in omega, because it is quadratic in Q, and Q is linearly proportional to omega, therefore it is also linearly proportional to omega squared. But this is just a kind of a quantitative feature with an unknown prefactor, which will be fixed by normalization. Okay? So we know that the capital D omega times small d omega is given by omega squared, the omega times the prefactor capital A, which can be fixed by normalization. So the way that we normalize this is by saying that there are a total number of 3n normal modes or phonon states, which is given by this integration over little d omega from 0 to the Debye frequency omega d, and within the integral we get density states capital D omega. And you plug in this capital D omega as a function of omega squared multiplied by unknown prefactor A, and you could verify that this capital D omega is given by this value, 9 times capital N times this h bar squared divided by kb theta and everything cubic times omega squared. So where we define this capital theta as Debye temperature, kb theta refers to Debye energy, which is defined by this h bar omega d. So h bar omega d is called Debye energy, and from Debye energy you can define Debye temperature because the energy unit is the same as what kBT, right? So effective temperature times the Boltzmann constant kb has the unit of energy, and that energy in terms of the Debye frequency is the same as h bar omega d. So then you could prove and derive this relationship between this omega squared and density states with a correct prefactor. And this will be your homework problem. So derive this relation. Let's take a short break. When we come back, we will plug in this Debye approximated density states back to the CV calculations. And then we could finally derive the thermodynamics quantities, specific heat as function of temperature. Okay, so let's take a short break.